There we go. Okay, so what's the verdict here? What's that sign? How do we deal with that sign? What do you think, Danielle? Nope.
Well, if we factor out, how do we factor out?
Can't factor anything out, you're right. Okay, now this isn't strictly speaking a rational function, is it? Because it's not a polynomial on the top. But it acts very much like one. Yes, sir.
Oh, I just thought I'd tell you.
Okay.
I got accepted to Linfield last.
Did you really?
I didn't even know I applied. I got accepted, and then I got a scholarship.
That's good news.
Yeah.
Very good news.
Yeah.
Furthermore, okay, so what do we do with this?
Should we turn the sign into?
No.
No, bad idea.
I don't know really how it was.
Is it relevant?
Well, I mean, we got to know what to do with it. Okay, now look what's happening. We're taking the limit as x approaches negative infinity, right? So let's look at the behavior of each of the terms in this thing and see what's going on. So what's going to happen to the 2x?
It's going to be
Okay, I mean, it's going to explode, right?
too positive.
It's going to get big. Positive or negative, we'll deal with that later. X is going to, well, as x approaches, yeah, quite big. So this is going to get big too, isn't it? Right?
Yes.
Okay, what about the sine x? What does sine x always do?
Be 0, 1, or negative 1.
If I graph y equals sine x, what's that look like?
It's a squiggly.
Yeah, it just, right? So it just keeps repeating, right? It's a wave train that just keeps on repeating. It's periodic, but it never gets very big or very small. The biggest it gets is positive 1. The smallest it gets is negative 1. So in the grand scheme of things here, when we're looking at the behavior of this function, does this even matter?
No, it doesn't.
Doesn't matter a bit. Doesn't matter a bit. It's not constant, but it's bounded. So it's going to get left behind when these other terms get really big, right?
Right.
So maybe it would be better to look at it like this. We could rewrite this as the limit of negative 2x plus sine x over x. And then this looks an awful lot like one of those rational cases we looked at the other day, the limit of a rational function. What do we do when the degree of the numerator and the degree of the denominator match? Yeah, just take ratio of the leading coefficients. Very good. So,
What did you say? If
The degree of the variable is the same. The highest degree of the variable is the same.
right, so if we look at the leading terms, I get x over
The
x.
numerator and the
Right.
denominator.
And so we just look to the ratio of the coefficients of the leading terms. So the answer is negative 2. Right?
Yes.
Make sense? Did it make any difference if we were approaching negative 1 or plus 1?
No.
No. Didn't make any difference because it acts like a rational function.
What if it was cosine? Same thing?
It doesn't make a difference. Cosine also would be limited.
So what do we find?
But tangent wouldn't, though.
Right? So we just found the limit. Now, if it were a tangent, this would have been, a tangent wouldn't really work because tangent is going to, if you look at what a tangent function
Lots and
does,
lots of asymptotes.
yeah, it does this, right? Just over, so there can be an infinite number of asymptotes, and so that function would never approach a single value because you'd keep getting these positive and negative infinities just thrown in randomly.
So would it be nothing or everything?
So it would be indeterminate.
Oh,
We couldn't figure out what it is. Okay. All right, so there's that one. Now, what about this guy? Let me make sure we know how to deal with one like this. How about I want the limit of
when the numerator is higher, it's 1, right? That's 1. Okay, it doesn't exist. When the numerator is low, whether
Snap with that one.
non-existent.
Right. Well, how about the square root? What do we do with the square root there?
X to the 1/2.
Say it again.
I know something.
Because this matches the case where, remember, if we take the limit of a rational function where the numerator is a higher order than the denominator, then there's no limit. It explodes.
And if it's the other way around, then it's 1, right?
Right. If the bottom
Is a higher,
is a higher order, then it's going to go to 0 because the bottom will explode faster than the top, and so the
Okay.
fraction
I
shrinks
got
to
you.
0. Okay.
So this,
Yeah.
this function goes to
This one goes to infinity. Yeah. Well, we'd say, okay, it's no limit, but then in Math Excel, they do something I like. They actually want you to put in an answer in terms of infinity, right? So we can do that. We could say, if we know that this is a no limit kind, and what about this square root, real quick? I want to deal with that. Negligible because square root is the same as x to the 1/2, right? Okay, so if this is an x to the 1/2, well, x to the 1 is bigger, and so that's still not the dominant term. That's the dominant term on the bottom, right? So all we need to look at when we're trying to figure out what's going on is the ratio of the leading terms, and the top one is bigger than the bottom one, so we know we're getting an infinite answer. Okay, as to the sign now, that's no limit, but if we want to be specific, we want to know which way is it blowing up. Is it going to be positive or negative? We just look at the signs of the terms. If x is approaching positive infinity, what's the sign of the numerator going to be? Positive, right? Because I get positive 3 times a positive number squared. Okay? What about the bottom? As x approaches positive infinity, it's going to be positive. Positive infinity is a positive answer. In fact, a very big one, right? So the answer is positive. Now, what if we were approaching, let's just change this a little bit. What if we were approaching negative infinity? What would that do to our answer?
Make it negative. Question mark.
So as x approaches negative infinity, what would the sign of the top be?
Positive.
Positive. Positive 3 times a negative squared is positive. What would the sign of the bottom be? Negative. So what would the overall sign be?
Positive.
Positive. Yeah.
Okay. Why would the bottom be negative?
Because if x is approaching negative infinity, then x is going to be very negative.
Oh,
Right.
okay.
Okay.
And no matter what on the top is.
Because it's squared.
Yeah.
Yeah. Yep. Okay. All right. Another one. So far, so good. Okay. How about this? Limit. Oops.
Oh, absolute value of 3. Oh, what are you doing here? Shenanigans.
Shenanigans, indeed. Okay, so this one, remember how we dealt with this? There's kind of a shortcut on this now. If we were to show this all algebraically, it'd be somewhat difficult to do. But we know that if we look at the dominant terms, the leading terms, on the bottom, it's that guy, right? On the top, it's the square root, isn't it? Right? The square root is going to be a lot bigger than the 4. But inside the square root even, what's the dominant player inside the square root? The x squared. Right? So I know that within the square root, it's the behavior of the x squared that's going to dominate. And so then overall, it's really just acting like 3 times the square root of x squared, isn't it? Right? Because this other stuff just doesn't matter so much. And the square root of x squared is what?
X question mark?
No. Absolute value. Right. The square root of x squared is the absolute value of x. So what this ends up looking like then is the limit of 3 times the absolute value of x over x
So it's always going to be positive.
as x approaches negative infinity, right? Okay, but now, and then here's where, remember, we get that weird behavior. If we graph the function absolute value of a divided by a, or vice versa, it's either 1 or negative 1. Right? It changes at 0. We don't even have to remember what it looks like, because we could just check. We know that when x is negative, right, what is the absolute value of x equal to?
Negative.
It's, well,
Wait, wait.
how do I say that?
I think last time I wrote this confused me too. So.
Okay, let's.
Smart more words, it's right.
Sure. Yeah, I don't want to confuse you. Okay, so when x is, let me write down the piecewise function for absolute value of x. Absolute value of x, written as a piecewise function, this will help,
No me gusta this one.
equals what? When x is positive, what is the absolute value of x equal to? X, right? It's not doing anything. Leaves it alone. But when x is negative, what's the absolute value of x equal to?
Negative x.
Negative x. Because I got to make it positive. Negative 1 times x. For example, what's the absolute value of negative 7? 7. So I must have multiplied negative 7 times negative 1 to make it positive.
What it is, it's asking what you multiply.
No, but think about it, because like if x was like -1, then absolute value of -1 would be 1.
Right.
So that
Okay,
would be
so I'd have to, you're right, but how did I get it from negative 1 to 1? I had to multiply by negative 1 to do that.
So we're not asking what it is, we're asking.
I'm asking what the piecewise representation is, right? So there's, okay, let me say that differently, right? I'm not asking you to evaluate
You gotta master the
the
piecewise.
piecewise function, or the absolute value function. I'm asking you to represent it as a piecewise function, right? So then, in the case that x is negative, we can replace this absolute value of x with negative x, right? Because for negative values, when x is negative valued, the absolute value of x equals the opposite of x, right? That's really what multiplying by -1 does. It gets the opposite, right? So then this looks like the limit of negative 3x over x, right? As x approaches negative infinity, and that's just the ratio of the leading coefficients, -3.
Wait, so it could be either -3 or
Well, in the case that we're approaching negative infinity, it's -3.
because
Okay, we need to see that one. That one's not sinking in. So get that one
The
again.
negative, I got the piecewise.
Okay. So then what we want to do is, and this is a general rule. Whenever we're dealing with absolute value functions or things of that nature, we always want to replace them with a piecewise function, because it's very difficult to do calculus or algebra with those absolute value bars there, because they mess things up. Right? It doesn't work normally. But if I think of that as a piecewise function, then I can just have one of the two pieces. Yes.
so why is the limit before it was negative? Maybe that's just
You have just contradicted everything I've ever learned about absolute value signs.
Why in the last step your x is going to positive?
There's a lot of questions.
Oh, negative. Sorry.
Okay.
And why is negative? Oh, because
Right? Because then that looks like a rational function.
that looks like one we can easily deal with.
Okay.
Find the limit.
Okay, I mean, there's a couple strategies you could use to get that answer. You could also just remember what this function always looks like, right? If I graph, and that's not a bad thing to remember. Yeah. So we know that
You like this?
the graph of both of those functions, remember, looks like this, right? Okay. So we know that function, the ratio of absolute value of x over x, is always negative when x is negative, and positive when x is positive.
Copy that.
Okay. But I mean, I don't know if I would. I think it'd be better just to. It's more pure and more general to think of it in terms of the piecewise function. If the absolute value of x equals that, now look where we are. If we're approaching negative infinity, then aren't we down here, right?
Okay.
Make sense? If x is approaching negative infinity, we're in this piece of the piecewise function, and that one we don't need.
I still don't understand why we don't, like, if the absolute value of 7 is 7.
Right.
Or -7, excuse me. The absolute value of -7 would be 7. So
Right.
why would you not put that in for the piecewise?
Well, we did. We did. If the absolute value, if I'm going to substitute a value for x into an absolute value function, like -7, right? think what a function does. I feed the function. Here, look at this function. This is a little lower level than calculus, but the idea is still true. If you dump a number into a function machine, it's going to spit out an output number. You feed it inputs, it spits out outputs, right? So, I mean, this worked out great because this is exactly what we're talking about. If I stick a -7 into the absolute value function machine, it's going to spit out a 7, right?
Right.
Well, how does it accomplish that? What is it? What's the formula that it has to use? It's got to multiply by -1 to make it positive. Ah, see? Yeah.
I was confused with
The
this.
function machines are manufactured by the
Yeah. Yeah.
So the reason why
Totally
you did
relevant
the
question.
negative X was it because that it's going to negative 7? Is that why?
Right. Exactly.
Okay.
Because right, and that's maybe I didn't emphasize that enough. If this thing is
My life is in the field of flowers.
And then on this vice function, you go to one that's going to the
Right.
That's it.
right, exactly.
That's complicated.
So because x was approaching -infinity, that's why we made this switch. That's why we were able to say that.
But if it was positive,
If it was positive, it'd be different. In fact, let's look at the positive case. What if we had?
Shouldn't have said that. Screw
You
it.
shouldn't have worried about it, Matt.
I was worried either.
What if we had this?
You really got to work on your red limit. 'Cause that looks like weird.
Yeah.
No,
Doesn't matter what we know
that
what it
means
is.
for read, no, that means for read.
So yeah. Oh, you know that. Oh. It's OIR.
Is that how you thought? I think that's it. Isn't it?
Google. That's how you actually spell Google.
Really?
Or if you're talking in terms of numbers.
Right.
Definitely in terms of franchise.
Don't worry about it.
Don't worry about it.
Don't worry about it.
It's not Ivy, it's Judy.
I don't know what that number means.
What number? Google.
You don't know what a Google is?
It's 100 zeros.
You
Google, yeah.
Is there an E on the end of that?
No.
Why don't you just write out?
That's
GL.
yeah.
Wait, whoa.
That's how you really spell it, Chad.
Oh, so they spelled it wrong on the website.
Well, they probably spelled it that way for a reason. I'm sure they didn't make a mistake.
They were just being silly.
They were being silly. Yeah.
Maybe Google was
Okay.
trademark.
So what about this one? Now, if x is approaching positive infinity, right? Oh, if x is approaching positive infinity, look what's going to happen. So the leading term on the top is just right there, isn't it? It doesn't matter how big these coefficients or numbers are. If x is approaching infinity, x squared dominates.
What if the number is infinity?
Okay? So,
Infinity is he's a sophomore.
She makes it know it.
Don't worry about it.
right?
I'm worried.
So far, so good?
Yep.
Yes.
Okay.
That.
If x is positive, whoops,
Wait, that's still negative, boss.
Where'd all the numbers go?
that's negative, that's positive.
They're irrelevant.
Yeah, so
because
it's
they
positive
go
too.
away as it goes to
Or negative,
infinity,
sorry.
They don't matter.
Right.
Negative 2 over 4.
Oh, and that's a good point. Is this some kind of an approximation that I've made here?
No.
Is that, I mean, I just lost that other stuff. Am I just saying it's kind of like this, or
No,
is it
definitely
exactly that?
Exactly that.
Exactly. As x approaches infinity, x squared becomes infinitely bigger than this other stuff, and so the other stuff truly doesn't matter at all. This is
It becomes
exactly
infinitely
equal
bigger
to
than
this.
the other stuff. That becomes infinite, but that's twice as. That's
Right.
Yeah.
Right. It runs to infinity infinitely faster, and so, right?
Everybody?
Right? Square root of x squared is defined as absolute value of x. And in the case here where x is, notice this, x is now positive, right? And so the absolute value of x, now we want this one, right? That one we don't care about.
Correct.
X is positive, so the absolute value of x can be replaced with a positive x. Okay? And so this whole thing just equals,
We talked about multiples now. Like we covered this stuff.
We did that.
right? That's it. So it's negative 1/2.
And how, you probably answered this, but how do you lose the absolute value sign?
You lose the absolute value sign because that. Okay, we want to think about the absolute value as a piecewise function. And because we're on the positive piece, you know, Right, we can replace it with x. If that had been a negative infinity, we would have had to have replaced it with a negative x. Okay? Good. All right, so next issue here now. Okay, this is something totally new. Very, very cool here. Now, what about this one? What if we have the limit of, let's say,
a new section?
yeah.
One section.
This is 3.6. This is the only really new thing in 3.6.
Dan's got it down.
To get prescription drugs included in that.
Okay, what about this? Actually, I can do this. I can say plus or minus.
That's stupid.
Okay, what about this? What's the answer?
Really?
Isn't it,
Say it again.
Jeez.
Hang on. Look at the order of the numerator, order of the denominator. Doesn't
Zero.
exist. Okay,
Zero.
blows up. Doesn't exist.
0.
Okay, but watch what we can do with this.
What, positive and negative?
Yeah, it could be either one. In this case, we're going to come up with a general answer for this. Okay, now there's no limit. Agreed, no limit here. But what happens if we divide this thing out? Let's actually take this quotient. Okay, you guys need to see this. If you don't see this, I'm not going to have sympathy when you can't do this later, because this involves a lot of review.
All right, why would we do that then?
Okay, watch. Watch what happens in this case when we simplify this quotient. We're going to divide this out. So we're going to divide 6x minus 1 into 2x squared minus 4x plus 3. Okay?
Oh, it's long polynomial division. You can know that.
So, polynomial long division, yes. Okay.
I know what's up with that.
Okay, so
No.
no, this is you have to be able to do this from now on in calculus, or you won't be able to do any calculus.
Polynomial long division.
So 6x goes into 2x squared. You know what? Let's start off with one that's maybe not quite that.
Yeah, I was gonna say you got fractions in but
Let's do one like this to start with. Later on, we'll deal with that. We'll deal with something.
2x.
1x.
2x.
Okay, so look at the leading terms. X goes into 2x squared.
2x.
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 Good. Right? So we get 2x, and then we distribute. Right? So we get 2x times x is 2x squared. 2x times 1 is minus 2x. Now notice something that's going on here. We're going to be lining up these columns, right, that correspond to the powers of the polynomial, right? Make sense? So that now think of the problems we would have if what if we didn't have a 4x term there and we just put the plus 3 right there? They wouldn't line up properly.
No.
We want the x squareds and the x's and the constants, etc., to always line up. So we got to think ahead when we're doing these kinds of problems using long division. We always want to leave a column for each different power of x. Now, if we skip a term in the numerator, well, then we'll just leave a gap there for it, right? Because there may be an x term that's being subtracted from that later. Okay. So now we're going to subtract, just like we do with normal long division. Of course, the leading terms have to cancel. That's why we picked 2x. So those go away. Negative 4x minus negative 2x is negative 2x. And then 3 minus 0, we just bring the 3 down.
Negative 2.
X goes into negative 2x.
Negative 2 times.
Negative 2 times. I distribute. Negative 2x plus 2.
Minus 1 over 5.
So those go away. 3 minus 2
1.
is 1. Good. Did I mess that up?
Yeah, I think you did. No, you didn't.
No, I'm okay. I'm okay. Yeah.
Okay, so that was good execution.
Yeah, perfect form.
Okay. So, yeah, there we go.
Great
So
style.
1. So 1 is my remainder, right? So then this thing ends up equaling. This is the same thing as saying the limit of 2x minus 2
The third limit of 1 over x minus 1.
Yeah, plus 1
So
over
instead
x
of
minus
just making
1.
it go to
You buddy.
0, or no, instead of saying it's undefined, you just write it like.
Okay, yeah, now what's that do for us? It's still undefined. As x approaches infinity, or negative infinity, this is going to be positive or negative infinity for our answer. So it's undefined. But look what it does. It creates an actual, as x approaches infinity, this last term would go away, right?
Virtually irrelevant.
And so this limit is actually equal to 2x minus 2. Sure, the x part is getting infinitely big, but the point is it's going to follow this linear pattern. So what we've really developed here is something called a slant asymptote. Yeah, it's going to cling to that line as it goes out to infinity, and it's still going to explode to infinity, but it's going to, instead of, like normally we would expect an asymptote in the past to have been horizontal or vertical, but they can be slanted like this too. Okay? And so if we draw this thing now, 2x minus 2, look what we get. Okay, let's go back to the original problem. Are there any vertical asymptotes in this problem?
No.
I don't believe so.
You sure?
Yes, there is.
Where is there going to be a vertical asymptote?
1.
Yeah, because that's where the bottom is 0, but the top is not 0, right? Yep. So we're going to have, if we make our little table down here, let's do this. We haven't done this for a little while. So we got our x, y, and we won't even do the y prime stuff right now. We'll get to that later. That's if we're just doing the asymptotes. And what we say was negative 1?
Do 1.
No 1.
1. Okay, out here at x equals 1, we had a vertical asymptote, right? So let's draw that in. Right? And we have the slant asymptote, which we can just write at the bottom here.
2x minus 1.
Y equals 2x, what was it? 2x
Minus 1.
Minus 1. So if I come up here and I graph that line, there's minus 1, 2x goes right there. So it's going to look like this.
Yeah, it is.
I know that my function is going to stick to those asymptotes. So it's still, this gives me a pretty good idea what's going on. I know that way out at the tails, I picked one with too steep a slope. But if I were to continue this way out here, I know that my function is going to do that kind of a thing.
Yeah.
Or it's going to do this kind of a thing, I guess. Right? Now inside in there, it might do other wacky stuff that we don't know about yet, but, right? But, I mean, we didn't worry about finding critical numbers and all that stuff. Okay. But you see where I'm going with that, though?
Yeah.
It gives us another guide to get the skeleton of our function. Okay?
That's probably a lot more practical than just vertical.
Well, it is. Yeah. Well, it's you can't always use it. It's only going to show up in certain cases. Now, what are those cases? When could you expect to see a slant asymptote? Yes. Say it again.
I don't get how you got the slant asymptote.
The slant asymptote we got because when we divided this rational function out, we simplified the quotient, this is the answer that we got, right? And in the limit that x is approaching positive or negative infinity.
Whoa. That's kind of cool. Like,
In the limit that x is approaching positive or negative infinity, that term is going to get extinguished, right? And we're left with this. Okay, well, that's the equation of a slanted line. And so that's that slanted line, therefore, is going to give us the behavior at the tails of the function. When x gets really big, it's going to stick to that asymptote. Okay? Make sense? No, vertical will be different. Vertical, we got that from right here. The vertical asymptote comes from this. The fact that there's a 0 of the bottom, but not the top. When x equals 1, the top is not 0 and the bottom is. So that led us to, if I take my arrow way down here, that led us to this conclusion. That when x is 1, we get a vertical asymptote. Okay? Now, one other really important question here, and then if we get this, we're in good shape for the day. How could we have known to expect a slant asymptote in this case, but not in, let's say, this case? If y equals...
Copy paste the other one so we can compare.
Yeah.
Oh, because there's a 3x to the 4 such way.
Okay. I'm going to put 3 of them up here, and I want you guys to tell me which ones have slant asymptote and which ones don't.
Do it.
There's exhibit A. Here's exhibit B.
Excuse me? Excuse me?
Here's exhibit C.
B has it, the other two don't.
Okay, B has it.
Correct answer is B, Bob.
Correct. A does not have it. Correct. C does not have it.
Correct.
Wrong.
Oh!
C does have a slant asymptote.
How
Why?
can you tell? Which
I
one
can
does?
tell by looking at it, and so will you be able to in about 10 seconds.
Oh, is it because there's
Is
negatives on the
Is it
denominator?
No, it has to do with the relationship between the powers of the top and the bottom.
Oh, and you can divide.
Ah, okay. If I divide
Yeah.
the denominator into the numerator, now what's going to happen if the top is x squared bigger than the bottom, if the order of the top is 2 or more bigger than the order of the bottom, when I divide this thing out, what's going to be the power of my dominant term?
Greater squared.
Yeah, x to the 4th over x squared is x squared. Now, there's no x squared in the equation of a line, right?
Wait, but isn't that how B is too?
Okay, but look at B. Now, with
I feel you.
With B, I've got an x squared divided by an x, and that's going to give me an x in the top, right? Okay. Down here, in C, x to the 4th divided by x cubed is still going to give me just an x, right?
So on the top is just X.
Yeah. So when it's a rational function, and the powers of the numerator and denominator, well, if the numerator is exactly 1 bigger than the denominator in power, then you know to expect a slant asymptote.
If you divide the top one, can we just factor the bottom one?
Okay, what would happen in the top one? In the top one, here's what you'd end up with. You'd end up with how do I describe this? You'd end up with a parabolic envelope for your asymptote. You wouldn't have an asymptote. You'd have something like this. If we were to look at the overall behavior, let's just say,
How did we get the mail?
it's a good question. What if in the limit of some function equals x squared, let's say. All the other stuff just goes away, x squared over 1. Okay? Then what you're going to end up with is something like this. You're going to get this parabolic. If I scoot out, pan out completely, here's the asymptote, which I'd call an envelope. And your function could do something really wacky inside here, but then eventually it's going to stick to this thing, right? Either up there or it's going to be down here, right? Yeah, but that's starting to get impractical because that's pretty hard to grab. Right? So a line's easy, and so that's why slant asymptotes are useful. Yeah.
What if I'm like circle asymptote?
You couldn't because then it's not a function.
Yeah, doesn't work.
Ooh, violates the vertical line test.
Yes, exactly.
So, what'd you get your well, that's a pretty big day.
Yeah. I can make you move, boys.
I'm best under pressure.